G'day, in this video we're going to be starting to look at circular motion and being able to describe that motion. So we'll be focusing on the velocity, centripetal acceleration and centripetal force of objects that are undertaking circular motion. So we're going to be looking at inquiry question 2 for the first time, dot points 5.2.1 and 3. Our key focus is to begin to unpack uniform circular motion. And in doing so, we're going to be beginning to employ some new formulae, which are actually quite closely related to formula that we used in Module 1 and 2. So our key learning intentions for today is to first introduce the concept of circular motion, define the term centripetal, and then begin to calculate the magnitude of velocity for an object when it moves through a circular path. I'm then going to actually show you how the formula for centripetal acceleration and centripetal force actually come to be, and we'll look at trying to apply that formula in a quick practice question. So first off, circular and centripetal motion. Generally speaking, we are assuming that if an object is undertaking some form of circular motion, it is moving in a circular path where there is a central point in the middle. At the moment, we are looking at uniform circular motion, so we are assuming that the object is moving at a constant speed. However, this will not mean that the object has a constant velocity. At any point on the path, as the object moves around, the velocity vector points as a tangent off the point of the circle that it is currently on. What this means is the size of each velocity vector should be the same because, again, the magnitude of velocity is the same. That's what's implied by constant speed. However, as we move around the circle, the direction of the velocity vector will change. You will start to see this keyword centripetal being thrown around quite a lot in this inquiry question. And what that suggests is that if we're describing something as centripetal, we're talking about movement that is going towards a central point. So in the case of our circular motion, we'll be talking about some sort of force or movement or action which is going in the direction of the central point. And we can see here in this diagram that acceleration points in this direction. We have centripetal acceleration. So in scenarios where you do have an object moving in a circular path at a constant speed, there will be consistent acceleration inwards towards the center of the circle. However, as the object moves around the circle, the direction of the acceleration will change as well. And we should note here that the velocity and acceleration at any one point in time should always be perpendicular to each other. Moving beyond that, we know that force is very closely connected to acceleration by Newton's second law. And centripetal force is the applied force on the object that is always going to be parallel to the acceleration. So if you do have an object which is accelerating inwardly towards a central point, then there's going to be some sort of force that's pointing in the same direction, which is causing this acceleration. It's the centripetal force and acceleration, which is what's leading to the object moving in a circular path to begin with. If there were no force or acceleration pointing in towards the center as the object moves around the circle, the object would just move in a consistent motion in the direction of the velocity. However, it is this force that's pulling the object forever inwards on the circle, which is actually making it move in a circular motion. So let's first look at velocity on a circular path. Applying some very basic kinematic principles, we know that velocity is equal to displacement on time. And generally, this is an average velocity, which will work quite nicely in these scenarios because, again, we're assuming that velocity is constant at all times. So really, to determine the velocity of an object moving in a circular path, we need to know how far is it traveling over what time period. And in order to do this, we're going to replace displacement for circumference and time for period, or the time taken for one full revolution to occur. Now, circumference may not be given to you in a question. However, radius is much more likely because this is much easier to measure. And based on some year 8 mathematics, we should know that circumference is equal to 2 pi times the radius, which means that if you know the radius, you can calculate for circumference. And then if you know the circumference and the time taken for one full revolution, the period, you should be able to calculate for velocity. In our practice question, we've been given that a toy train is placed on a circular track with a radius of 1 meter. We're being asked to calculate the velocity of the train if it completes a lap of the track in 33 seconds. So in order to calculate for velocity, we'll substitute in our values to our formula and then calculate. Now this comes out to 0.2 meters per second to one significant figure. Now calculating centripetal acceleration becomes a little bit more interesting. And in order to determine the formula, we're going to need to do a little bit of vector analysis. In this first diagram, we're being shown two separate points that represent an object undergoing circular motion and both its position and velocity at two different points in time. This gives us vector v1 and v2. Now, considering that average acceleration is the change in velocity over time, when completing vector analysis, we can say that the change in velocity could be simply v2 minus v1, both of which are vectors, which means that we can do essentially a vector sum here. This needs to be rewritten as the vector of velocity 2 plus the negative vector for velocity 1. And that's exactly what we see here being shown in part B, where delta V is the sum of V2 and negative V1, and the angle between V2 and negative V1 is simply theta, the angle between both points where the object is undergoing velocity 1 and velocity 2. Note here that the change in velocity vector is parallel to the acceleration experienced by the object. Now, something that's interesting is when we look at this vector triangle and compare it to another vector triangle which can be made with the radii between the central point and the two locations of the object, and then the displacement which connects the two, we now have two similar triangles, meaning that the sizes of the sides of the triangles may not be the same, but all of their angles are identical. And we can tell that this is the case because we have an isosceles triangle where the angle between the two equal sides is the same angle, theta. And something that you may remember from year 10 maths when looking at similar and congruent triangles is that the ratio of a pair of sides in each of the similar triangles are going to be equal to each other, meaning that the ratio between these two sides, the displacement and r, is going to be equal to the ratio of these two sides, the change in velocity and velocity 2. In this case, we're going to rewrite the displacement as velocity times time. This is going to enable us to produce our centripetal acceleration formula. So we know that velocity times the change in time over r is equal to the change in velocity over velocity. Now from this point, what I'm going to do is rearrange the equation so that we have v times v on r on one side and change in velocity over change in time on the other. Now this here is equal to centripetal acceleration, because as we know, acceleration average can be equal to delta v on t. What this gives us is that centripetal acceleration is equal to v squared on r. Now this proof is a little bit involved and there's a couple of steps to it. I'm happy to discuss it further in class, but for now let's just have a look at applying this formula to our train problem. So again, we've been told that a toy train is being placed on a circular track with a radius of 1 meter. We're being asked to calculate the acceleration of the train as it completes a lap of the track in 33 seconds. So we know that the time for one full revolution is equal to 33 seconds, and we know that the radius is equal to 1 meter. And based on our previous calculation, we also know that the velocity of the train is approximately 0.2 meters per second. With this information, we can calculate for centripetal acceleration, which is equal to v squared on r. So the direction here doesn't matter so much. We're just concerned about the magnitude of the velocity and the magnitude of the radius, as this is going to be able to give us the magnitude of acceleration. So what we'll do is we'll substitute into our equation. So 0.2 square on 1. And this gives us 0.04 meters per second square to one significant figure. And here, if we were to report a direction, we should show that the acceleration is always towards the center of the circle. Now, finally, we have centripetal force, which is simply a combination of our always favorite Newton's second law, which is that F is equal to m times A, and that centripetal acceleration is v squared times r. All I'm going to do to show you how to determine centripetal force is to substitute our centripetal acceleration value into the F equals ma equation. So let's have a go at trying to actually implement that equation into our practice question. So in this case, a toy train, again, is being placed on a circular track with a radius of 1 meter. We're being asked to calculate the force applied on the train if it completes a lap of the track in 33 seconds. So in this case, you'll need to know a mass value for the toy train. Let's just say that it is 0.5 kilo. So to extract some of our data from the question, we know that mass is 0.5 kilo. V equals 0.2 meters per second, and R is equal to 1 meter. So let's substitute in and calculate. This should give us a value of 0.02 newtons, correct to one significant figure. Again, this force is always pointing towards the center of the circle. Thank you very much. In the next video, we'll continue to build on some of these circular motion concepts and start to look at angular displacement and velocity. But until then, have a good one.